In this fifth guided review problem for shear moment diagrams, things get a little bit wackier. We're given the responsibility to do a lot more on our own. We're not given very much information here. So, we got lots of loads. We've got a 400-foot kip positive moment, clockwise moment, smiley face moment here. At the far left, we've got an upwards triangular distributed load. We've got a uniformly distributed load in the middle portion, and we have a 30 kip concentrated load. Notice this is a diving board with a very complicated set of loads, and nobody's given us reactions. So we need to find those reactions right off the bat. Let's label this A, B, C going across, so we have reactions at B and C, and I'm going to guess that the reaction at C is upwards positive, and don't know what's going to happen here at B just yet. So let's do this. Let's sum moments about point B. Let's take clockwise positive. So we'll have 400-foot kips plus, we got to find the resultant of this triangular distributed load. That's 1/2 of 10 kips per foot times 6 feet. Its moment arm, well, centroid here will be at the 1/3, 2/3 for that triangle. That would be 4 foot over. So 4 would be for that one. That's all again going in a clockwise fashion. And then we got the distributed load at 10 kips per foot times 10 feet. Also clockwise. Its moment arm, see 10 feet, so its moment arm is 5 feet from B. Plus then the 30 kips times its moment arm is 6, minus 10 times CY, all equal to 0. And let's take a look here. Then we've got 400 plus 0.5 times 10 times 6 times 4 plus 10 times 10 times 5 is 500 plus 30 times 6 is 180. That all equals then 1200, and that'll be divided by 10. CY is equal to 120 kips. Let's check out real quickly here. Sum of forces in the Y, we'd have going down 30 plus 10 times 10, that's 130. Then over here at the left, we got that load going the other way, 0.5 times 10 times 6, a net of 100 going down. So that means that, did I do that right? No, I didn't include the 120. Yeah, so that 120, that's 100 going down, 120 going up, that's a 20. That probably, oh wow, looks to me like BY has to be going down. And I'll assume that. Let's verify this by taking sum of moments about C. We'll take clockwise positive again. 400 plus 1/2 of 10 times 6 times its moment arm is now 10 feet plus 4. Plus, then we got the distributed load here, that's 10 times 10, its moment arm is again 5, plus 30 times its moment arm of 4, and then subtract off 10 times BY, set it equal to 0, and we hope BY turns out to be 20. Let's see if it does. 400 plus 1/2 of 10 times 6 is 30 times 14 plus another 500 plus 120 equals, divide by 10. What did I do wrong? I got all kinds of errors in the signs. That's what I got wrong. Now I'm actually kind of doing this on purpose so that you can see we got to be careful and thoughtful about how we're doing all this and how you check things so that you're not reliant upon carryover partial credit. So 400 plus 30 times 14 minus 500 minus 120 equals 200 divided by 10 equals 20. That's what it was supposed to be by sum of forces in the Y. Wow, that was a lot of work just to get the reactions. Now, this is a complicated problem. Now we can go fuss around with the shear moment diagrams. This will be challenging too. dV dx equals Q Well, Q starts off with a positive intensity upwards, 10 kips per foot, and then goes to 0. So we're going to have a second order curve that's concave down. How do I know? Well, I'll take a look here. We've got no reaction here, so that's going to be, then, let's see, that change, that area, the area was 1/2 of 10 times 6. That's 30, so it's a plus 30. So about to there, second order curve, and that second order curve means we end up with 0 slope there at B. Okay. Then we have a sudden change in the slope. We go down 20. 2 plus 10. Then, wow, this is going to be quite something here when we get to the moment diagram. Then we're going to go 10 kips per foot, so it's going to take us 1 foot to get over to 0, but let's see, over to here, that'd be 10 times 6, that would be 60, so we're going to get to minus 50 as a net. Not particularly really drawn very well. That's 1 foot, and we're at minus 50 here. We have a sudden change from the shear that takes us to minus 80, and then we continue that slope, 10 times 4, that's another 40 to take us to 120. And then we have the 120 reaction that takes us back to 0. Wow. That looks ugly, but it is the right kind of shape. And now, now we got to get the moment diagram in. All right, let me zoom out a little bit here so we can see all of it. All right, start off at 0. We immediately go up to a happy face 400. Clockwise, positive moment there. So there's your 400. Now we're going to integrate a second order and go to a third order. So we're going to start off with 0 slope because dm dx equals v. Right? We're not looking at the slope of the shear diagram. We're looking at the value of the shear. The shear is 0, so we start off at 0, and then we got to go get that area. Now, I happen to know that that will be 2/3 of the base times the height, or you could go and do a free body diagram right to the left of B, which is what I'm going to suggest that you do, not take the shortcut that I know is actually available, because I know these areas of these parabolas. So there's your 400 foot kip there, there's your 10 kip per foot load, and there's our positive shear, there's our positive bending moment. With some moments about this point, which is point B, and you'll get that 400 plus 1/2 of 10 times 6 times a moment arm of 4, and that's 30, oh, that's 520, and that will turn out to be positive. So we actually went up to 520. Right, so note here, 2/3, 30 times 6 equaled 180 times 2 divided by 3. That was 120 increase over the 400. Look up these kinds of things and you'll find out that this kind of special parabola, that area would be 2/3 of the base times the height. Again, we have 0 slope at the beginning, we have a positive slope at the end, and we're up to, at that point, 520. Then we have a different, we go from third order to second order. Its maximum happens right here, 1 foot to the right of B, and that's an easy area. That's 1/2 of 1 times 10, or 5. So we're going to go up to a maximum of 525. We start off at a shallower slope than what we started at to get there. Right, so we're at 520. We'll go to 525 with a second order curve. I'm not going to show it yet. I'm just going to get my third point, which is over here. This is 5 feet over, right? 6 feet total, 1 foot already taken up, so 5 feet over. So this area is 1/2 of 5 times 50, so that's 250 divided by 2, that's 125. That takes us back down to 400 right at that location. And so 5 times 50 equals minus 125. I need a little tiny second order curve to get in here. This is not going to be easy to find the right kind of second order curve on the French curve, but this is looking pretty close. Notice my little break in slope that we have right here because the shear is discontinuous across that point. And we're also going to have the same kind of thing happen to us right there. There's your extended tangent coming from the left, but this one, we pick up a bigger negative slope, right? And the average, this trapezoid here is, give the average height times the width. It's 4 feet, average is 100, so it'll be a minus 400. That takes us to 0. I like that. And it's got to be a second order curve. And so we will show that notionally. Like that. Hard to see that break in slope, but it is there. And we'll show the extended tangent to make it clear that it really is there. And there you go. It needs to be cleaned up, but as a quick dirty sketch, there you go. There's your shear moment diagram for this complicated problem.